So in the first part, we have now seen what activation functions we're looking at, how the gradient distribution for the input-output looks like. And now in the second step, we will actually train different neural networks with these activation functions and then try to analyze, okay, what is actually going on in the networks, how do these activation functions influence our training. What we will do for this is we define a neural network. So we will use here simple linear neural networks and actually train it on the image classification task. So let's maybe first start with defining our neural network. I've already seen in the Python tutorial how you define a general neural network or a small linear network for a very simple task, while here we make it a little bit more complex. So we take here as input arguments the activation function we want to use, the input size, so number of input units. 784 is because of our data set, which is 28 times 28 pixels. Number of classes we want to predict, so we're not doing here just binary classification, but actually multi-class classification. So we have here 10 classes in our data set we will also take a closer look at later. And we define here a list of hidden sizes. So if we say here 4 hidden sizes, we'll have the 4 linear layers plus then 1 linear layer to the output, to a classification. And these numbers in here indicate how large or what hidden sizes we basically want in these layers. To do this dynamically, so you have seen, you can of course now say in a module we have here self.linear1 equals self.linear2 equals this, but you see that it's not really flexible if we have here a list of hidden sizes. And therefore, PyTorch usually provides functionalities like nn.sequential. And nn.sequential takes a list or then multiple modules as input and stacks them together as one module where each of the inner modules are then executed one by one. This is why if we do it here, for example, first define, okay, what are our layer sizes? So we can say for each layer index, we start by what is the input of this layer, what is the output of a layer, apply activation function, and do that a couple of times. So for this input here, we will run this loop 4 times. So the first one will have as input 784, as output 512. Then we have activation function. So next we will have input 512, output 256, and so on. And then the final one will take what we have here, 128, and maps it to 10 outputs. And if we do then end sequential with the asterisk here, meaning that this list is then spread into arguments, that we have then basically one module which executes all of these layers in sequential. Again, just have here config to save the hyperparameters so we can store them and load them later. The forward function is quite simple. So as you know, image is usually multidimensional, so we have height, width, and channel size. But if you take it into a linear network, we just view it as a vector. So we stack all the pixel values in one vector and put that basically through our neural network. This is why if we say now x.view, x.size0 is the batch size, times then the size of the images. Then we can just say out.self.layers and we'll get then prediction for the 10 classes for the inputs. So let's run it. Below here, I've defined now a couple of functions for loading and saving the model. I don't want to go into too much detail here, so if you're interested in it, please take a closer look. In general, what we do is when we save a model, so maybe first look at saving, we first save, save here the state, as you know, the parameters of a model, so all something we have optimized, or we save here basically the hyperparameter configuration. That's just a good practice to do, because when you want to load this model, so this static, you should know what, for example, what activation function you have used, because this is not in the static as it's not trainable. While in loading then, we basically load first the hyperparameters, create a neural network and based on these hyperparameters, and then load the static. We can also run it just here, so we can load our models later. Next, we use actually a different package now from PyTorch, another one called Torch Vision. Torch Vision is basically addition to PyTorch, which specializes on vision, computer vision, which has then multiple operations for it, as also, for example, data sets. It provides for common data sets you can just find in Torch Vision and directly load, from which we also use one, namely Fashion MNIST. So Fashion MNIST is basically similar to MNIST, as you know, but it uses clothing instead of just digits. We can shortly first visualize before then taking a closer look at the code actually here. So you see that if you say the data set in Torch Vision, it basically also allows you to automatically download it. So the Fashion MNIST, as you can see, has now here these different inputs, and then it has a sweater, shoes, trousers, and so on. So these also will be then our 10 classes we want to classify, and it's just a bit more harder than simple MNIST. Let's take again a look what we have done here with a data set. So for Torch Vision, there's also something called transforms, or basically transformations. These transformations are then small operations that are applied on the image before returning it in the data loader. So what we do here is, as the images are first NumPy arrays or different objects, we first transform them into a tensor, and then we do here what we call a normalization step. So basically what we do is I subtract 0.5 and then scale by 2, which takes the image which we have between 0 and 1 and will then scale it between -1 and 1. Because it's just better, as you will have also seen in the next lectures, that normalizing the data, or at least having it between -1 and 1, is significantly better than just 0 and 1. So now we have a data set. We also have the model. Now we can start to actually look into the parts we want to do with our activation functions. So one thing we should think about is, let's look at the gradient distribution throughout the network. So we will take a network, define an activation function, just have it initialized by PyTorch default. We will look also at initialization in the next tutorial, tutorial 4. And then we will basically do one backpropagation step to calculate the gradients for a random batch and see how the gradients actually look like across layers. Because optimally, we would like to have a similar gradient distribution for each layer. So for this, I basically defined here a small function where we take a network in. We take here one single batch, which is a bit larger. So here I use a batch size of 256, just for more batches, or the more elements we use, the larger than the batch size, and therefore also the more accurate the distribution of the gradients will be. We need to take then basically one forward step. So we first do 0 grads. We can also do it before, lost it backward. It doesn't matter where we put it. We do the prediction. I use then here the torch.nm.function functional package for using then f.cross entropy instead of defining an extra module for performing cross entropy. Perform one backward step, and then I take the gradients we basically got here. Here it looks now a bit more complicated, but I will go through with it. So grad.data, basically I say, okay, I don't want the gradient tensor, I just want the data in it. .view -1, so I take the batch dimension times the parameter dimensions and just say, okay, all is 1, because I just want a distribution for 1 per layer instead of having per single parameter or so on. When I put it to CPU, so if it was a GPU, put it in CPU. In case it has been already in CPU, you need to make sure that you also clone it, so that you have a separate, and then you can take a numpy .numpy operation, which basically takes a tensor and maps it to a numpy array. Then I just add the name, so we know actually which layer it was, and then I plot this as a distribution. So let's do that for all our activation functions. So in this loop, I basically define always a network, choose then one of activation functions, and visualize the gradients for this specific network and this specific activation function. this loop also takes a while because of the plotting, which is a bit slow here. So the first one is already shown, which is the sigmoid. So the sigmoid, we have already seen the highest gradient is 0.25, which would let us expect that actually the gradient will decrease over layers, and this is also what we see here. So the input, you see we have a gradient distribution between like 0.05, while here in the input it decreases all the way to minus 1 e minus 5, which is very small. And the issue then with such a very different gradient scale is what learning rate do you use? Because for this layer you would need a very small learning rate, while for this one you need a very high learning rate to actually learn the network. And this is already an issue with sigmoid, which is why it is usually not used in deep neural networks. The tanh you see has a much smoother gradient distribution, so it is quite stable across layers. Of course, the first one is a bit higher, but this also because it's smaller and it's directly to the output. It also actually depends on the initialization. We'll talk about it later, but also the initialization which PyTorch uses by default influences these gradient distributions slightly. ReLU, you also see, has a huge peak actually at 0. This is because, half of the gradients are mapped to 0, right? Or in expectation, half of them, and therefore we usually have a much more peaked distribution, especially in the beginning. But this is not a problem as long as it's peaked for each layer. So you see it's actually peaked around the same with the same variance as we have here. The Leaky ReLU is not very different, so we used here also relatively small negative slope. So it is slightly wider. Well, the ELU you see is already much smoother because it has not this very tiny gradient, but the gradient just converges to 0 in the negative part. And Swish has a similar distribution here, while it's also relatively stable across layers. So after we have seen that, we can now see, okay, so in our expectation, actually all activation functions perform well in terms of the gradient distribution except for sigmoid. So what happens if we actually train a model exactly the same, with exactly same hidden sizes and so on, but using different activation functions that we can use here? So I defined here a training function, which you can also go through in detail shortly. We have here a SGD optimizer, we use cross entropy loss. We then have here our training loop, where we basically can push the layer to GPU, push then our model through, push the input through the model, calculate the loss that backward, optimize that step, and just record here some metrics, which is good also to know, for example, the training accuracy, or also the training loss. And we do then here validation, while in the end, we basically load our best model and test it. And the test function or the evaluation function is also very similar as you have seen in the PyTorch tutorial. Basically, again, take with torch.nograd to have no gradients here. Take then the model, push through the input, take the argmax of the last dimension. We don't have to apply a softmax because the argmax over the softmax or argmax over logits gives us exactly the same result. And then calculate here the accuracy. And this is also what we return as the test accuracy. So therefore, let's run our models. We have here already a pre-trained one. This is why we just load the pre-trained model and then test it. This is much faster than if you would have trained all from scratch, because that takes some time. Also, the networks are relatively small. So what you can see here is that the sigmoid activation function is failing to actually train a network properly. So 10% is random chance. So it doesn't really improve above random. While all the other activation functions get similar scores. So you see that tanh gets 87.5, while then the best one here, Leaky ReLU, gets 88.9. There is basically, you could now say, okay, in our experiment, Leaky ReLU is the best, but that would be a bit too fast because this is just a single one. There is a lot of randomness also in it. So these differences are actually not large enough or significant enough that you can directly say, okay, leaky ReLU is the best. What you can do is, of course, you can run these models then for multiple seeds, multiple initialization, multiple data shufflings, and then compare them. That's usually how you do it also in the paper, and then say, okay, this is significantly different than the other one based on the distribution of scores we got. However, it doesn't really make sense to do it here because it just takes us a lot of time. Well, the activation function, a lot of people have already done that with a lot more resources. But you would only get a result for this specific activation function, for this specific network, for this specific dataset. And we would be rather interested in what if I have an arbitrary network, an arbitrary task, what activation function should I use? And there you already see, so in general, any ReLU-based activation function usually works well, while some are preferable for very deep neural networks. So finally, we also visualize here the activation distribution. So what we do is, again, take a batch, push it through the network, and visualize the distribution for the activations we get out. So it's, again, very similar. You can see I just push the batches through it and then store the activation values. So basically the values I get after applying the activation function in each linear layer. And if I run it then here, you will see that we'll get, again, very different functions or distributions also across activation functions because they have different input-output mappings, right? So this is why we should expect that especially the sigmoid probably is not really learned much. So you can see here, for example, it didn't really do anything while the outputs here are somewhere between 0.4 and 0.6. So it's basically just around 0 because it is actually losing all these gradients, right? And the input basically didn't change much. The TAN-H, you can see it's actually quite interesting. Well, the first layer has these peaks around -1 and 1, probably because it just looks in the input image and checks then for specific features, which these indicate. While then for the center layers, we see that it actually uses less these extreme points of -1 and 1. And again, the output, so the layer before mapping to the classes has again these maximums because this is really where it then gets important which class will be then basically our prediction. The ReLU is, as expected, has a high peak around 0 with actually a long tail. So that's also something to think about. While, for example, here, the TAN-H always has a maximum of 1. The ReLU can get quite large, up to here actually 10. But also another interesting feature is here that the output of the linear layer, so before I apply the ReLU, actually also has a bias towards positive. This is because it doesn't matter if the linear layer outputs -1 or -2, -5, because in the ReLU it's always 0. So therefore it doesn't get any gradient signal to push these values to even lower ones. The leaky ReLU is very similar with a slight addition to the negative, right, because we have a negative slope here. The ELU is much smoother, as you can see here, so it's really at 0 and then comes this exponential decay, which it uses, so therefore it also has slightly more smoother curve. And the swish one is actually also very similar to the ReLU, with a slight addition here to in the negative part. But what is actually also often seen is that in swish you get even higher values. So here you see we're even above 10 than in a normal ReLU. Just again something which swish basically has a characteristic. So therefore, if you have now trained all the networks, you see that all the ReLU based and also TAN-H actually performs quite well. For a very deep neural network, however, there are different disadvantages. So TAN-H is good when around 0, but as you see, if it has these peak values, also gets very fast to a gradient of 0. ReLU has the known problem of dead neurons, which we look at here below, and therefore it's often advised to have something like a swish activation function for very deep neural networks, because they give you a non-zero gradient for the negative ones, while it still has this characteristic of ReLU and has shown to work actually quite well. So now we can look at dead neurons in your ReLU networks. So as you know, ReLU suffers of this problem by having neurons which just don't get any gradient signal. So it's basically the input to the ReLU is 0 or negative for every possible input in the data set, and therefore we don't get any gradients back for these parameters and can't update it. Therefore also this neuron is useless for the network because it's always 0, right? It doesn't give us any indication what input we are actually looking at and what class it might be in. To identify this problem or how serious this problem actually is in a neural network, we can do here a small test. So what I do here is basically I take a network, we then decide which one it is, and we push then basically a batch, or actually all the training examples in our training set, and check for which of these ones is the neuron 0. So basically for which of them are we not getting any gradients. And if we get the neurons which are 0 for every possible input in the training set, we know this one is a dead neuron. And we measure it here to then see, okay, in our network, how many dead neurons do we actually have? So how serious is this problem? It's again just a bit of code. In PyTorch, feel free to take a closer look, but it's not, let's say, too exciting or too different than you have already seen. So let's start by initializing here a random neural network with a seed so we can reproduce it using a ReLU activation functions and check how many dead neurons it has over the layers. So here we then push all our data through. That takes a few seconds, and then we'll finally get out that we actually see, okay, so in the first 2 layers we don't have any dead neurons, while in the last 2 we see it actually increases. So first have 3 and then 10, which is about 8% in the last layer. However, one thing you should also remember is that ReLUs, so dead neurons in the last layers, can be reactivated because the input to these layers are changing based on the previous layer, right? So basically, if I optimize layer 2, I change the input to layer 3, and therefore dead neurons in layer 3 can be again reactivated. Therefore, if we have G10, if we now actually check what did our pre-trained model, so if we have trained our model, how many dead neurons do we have in there, we will actually see that multiple neurons have been reactivated, so that we probably have less neurons dead, and exactly this is what happened. So in the third layer here, we have now non-dead neurons, while in the last one we have 3, so also very minimal. There you see that actually these dead neurons is not a problem for a small neural network. However, if we look at a deep neural network, so here I took just a neural network with 10 layers, stacked them all together in a linear network, and let's check how many dead neurons do we actually have in there, because there it might be more serious the deeper we go. There you see that actually, especially in the late layers here, we have a lot of dead neurons, and this is also, of course, this again depends on the initialization and all the different factors we use here. However, we can already say that the deeper you go, it also has some probability to have dead neurons, and especially if you now have this starting condition, you see that a lot of neurons need to be reactivated while you start training. This can be a bit tedious and also give you some troubles, especially in deep neural networks, and therefore it is their advice to use a swish function or a ReLU-based activation function, which can have also gradients for the negative part, so you don't have dead neurons. So this is already then the end of the tutorial here. So we have seen different activation functions. We have looked at sigmoid, tanh, ReLU, licky ReLU, ELU, and swish. Of course, feel free to just add another activation function, train your own network, and you can do the whole code again from top to bottom, visualize the gradient distribution, and so on. As a conclusion, we can really say most of the activation functions we have looked at here work well, especially in linear networks, If you go to convolutional neural networks, usually a ReLU-based activation function is the common way to go. And if you go very deep, then you should look into functions like swish or similar. So there's also some activation function called GLU, which is used in other networks, and this is actually very similar to the swish activation function. So therefore, in the next tutorial, tutorial 4, we'll then look at initialization and optimization techniques for the neural network.